So on Monday we started quantum statistical mechanics, and the main tool that we are using was the density matrix. Well, it's basically another formulation of quantum mechanics, which is a bit more general in the sense that it can also be used to describe systems that are interacting with an environment. So in such a case, if your system is interacting with your environment, the whole system, the system plus the environment, might have a wave function. If it has a wave function, then your system separately doesn't have its own wave function. So you cannot really talk about the wave function of your system without considering the environment. But you can still define the density matrix of your system plus the environment as just this operator. And now you can obtain a density matrix for your system only by just taking the so-called trace over the B degrees of freedom of the combined system. And what will happen is this will be just a sum over Pn times some states phi n. What this is, your system now, you cannot really say about the state of the system, but it will be with a probability Pn that your system is in this state phi n. And keep in mind that these phi n's, they don't even need to be orthogonal to each other. Some general properties, we said that trace of rho is always equal to 1. Basically, this is the normalization. The total probability has to be 1. And the trace of rho squared is less than or equal to 1. And so we have two cases here. One case, trace of rho squared can also be 1. But if you imagine rho to be a diagonal in some basis, then rho squared will be just a matrix with the diagonal elements squared. Well, the diagonal elements are basically the probabilities, which are less between 0 and 1. So if their sum is 1, or let me put it this way, Pn squared is always less than or equal to sum over Pn, since Pn is some number between 0 and 1. So if you take it square, it becomes a smaller number, unless it is 0 or 1. If it is 0 or 1, it remains as it is. So if trace of rho squared is equal to 1, it basically means that one of those diagonal elements is 1, and the other ones are all 0. So this is when the system is in a pure state. And you can talk about the wave function of the system. The system definitely has a wave function, which corresponds to that 1 in the diagonal. And if trace of rho squared is less than 1, strictly less than 1, not equal to 1, then we say that the system is in a mixed state. For such a system, we can ask the question, for example, what is the probability that an observation will say that the system is in some state, let's say phi m. This probability is nothing but the diagonal element. This probability is phi m rho phi m. Just the diagonal elements give me the probabilities. And average of any quantity, or the expectation value, this will be given by trace of rho times O. Okay, these are things that we had seen on Monday, and that is more or less where we had left. Well, up to here, I'm not doing any statistics. I'm just doing some quantum mechanics with an alternative, within an alternative framework. So any questions up to here? Now I can start talking about my ensemble. Basically, I have my system, many copies of my system. Each one of these identical copies of my system. Each one of these copies will have some density matrix of its own. And so the density matrix of the ensemble is basically just the average over the ensemble. This is the ensemble average. Now the next thing we will do is, okay, so we define the density matrix, we know how to use, etc. But what is the density matrix? How can we obtain the density matrix for, I don't know, microcanonical ensemble, and grand canonical ensemble? So let's start with saying that, okay, the density matrix will be its time derivative, let's say 1 over n k 1 to n rho k dot. So let me look at the time evolution of the density matrix of a single member of the ensemble. And remember, this density matrix will be sum over n p n times phi n phi n. So I need to take the time derivative of this operator. Now, if you remember from quantum mechanics, you have various pictures to describe your system. Frequently, we work in the so-called Schrödinger picture. In which the states are time dependent, operators are time independent, in the Schrödinger picture, density matrix is time dependent. So although it's an operator, it's a time-dependent operator in the Schrödinger basis, in the Schrödinger picture. Well, it's not a big surprise. It's basically the wave function itself. The wave function is replaced by the density matrix. So if the wave function is time-dependent, then rho is time-dependent. So although now I'm looking at the time dependence of this operator, I'm actually working in the Schrödinger picture. So rho kt, well, let me drop the k. Rho t will be whatever probabilities I have created my system in phi n of t, phi n of t. So the time derivative will be equal to Pn, the time derivative of phi n of t, the ket, plus the bra, the ket times the time derivative of the bra. Let me just multiply with IH bar also. Because now I can use the Schrödinger's equation. Schrödinger equation tells me that IH bar del by del t of phi n of t is just h phi n of t. And also minus IH bar phi n of t d by dt is equal to phi n of t times h. If I use it in the above equation, what I would get, the time derivative of the density matrix itself is Pn h phi n of t minus phi n of t times h from the right. But this is just h rho minus rho h. or the commutator of H with rho. This is true in general. Whatever the system is, whether it's in equilibrium or not, I don't care. This will be always true. I didn't make any assumption now. But if the system is in equilibrium, d rho by dt should be 0, and hence H and rho should commute. But if H and rho commutes, well, this basically, at least one way to satisfy this is rho is actually a function of the Hamiltonian itself. So if you compare it with our Liouville theorem, in the Liouville theorem also we derive such an equation. There we had the Poisson bracket of rho and Hamiltonian. Well, quantization, here now we have not the Poisson bracket, but the commutator of the Hamiltonian and rho. That's the main difference here. And again, in that case, since H commuted with rho, we had said that, okay, rho is a conserved quantity. Choice here, rho is a conserved operator. It doesn't change in time. Well, in that case, we could say that rho is an additive conserved quantity, so logarithm of rho is logarithm of rho is an additive conserved quantity, so it had to be a superposition of E, all the other conserved quantities, etc. Here, I mean, we won't be repeating the same arguments here. It's enough to say that, okay, rho is a function of energy. Rho is a function of the Hamiltonian. In the energy basis, rho will be diagonal. So rho commutes with H already tells me that rho can be diagonalized in the energy basis. So in a basis in which HMN is equal to En Kronecker delta Mn, rho Mn will be just rho n, some function of energy, Kronecker delta Mn. They can both be diagonalized at the same time.
Hocam, in that theory, I could enunciate it, but we had explicit time derivative of the observer, but in that case, will we have some
in this case?
Yeah.
Well, let's see. What are PNs? You might say that you might have a system such that PNs are time dependent. Here I assume that PNs are already time independent, they are fixed. So here there's no way that I can have an explicit time dependence if PNs are independent of time. In that case, we said that the total time derivative was 0 because of the conservation of the number of copies of the ensemble. And so we had a relation between the partial derivative and the Poisson bracket. Here, this total derivative is actually the partial derivative over there. You see, this is now a total derivative because it's an operator, it only depends on t. If I would write, I don't know, the matrix element of this one in the position basis, then that matrix element will depend on the positions, and this would have been a partial derivative. So, now then, what is this rho? And we have the microcanonical ensemble. Then rho n of E is equal to 1 over gamma if n is an accessible state and 0 otherwise. What do you mean by accessible states? Well, we have conservation laws. So rho n of E would be, for example, 1 over gamma for the states that have energy equal to E, and it will be 0 for other states if En is not equal to E. And once you know what your rho n is, you can determine gamma, and the entropy will again be k times logarithm of gamma. If this is, let's say, a pure state, in that case, gamma would be just 1, and if it is 1, the entropy is 0. So we have all the properties that we had tried before. Then we can talk about the canonical ensemble. In the canonical ensemble, rho n of E is e to power minus, no, sorry, rho n is e to power minus beta En. Well, that E is kind of superfluous because N already specifies the energy. N is the state, so it specifies the energy of my system. So this is the canonical ensemble divided by, of course, the partition function. Now the partition function is sum over all the states my system can be in e to power minus beta En, but this is sum over n e to power minus beta n, which is nothing but the trace of e to power minus beta h. Rho, let's say this is rho n in the energy basis, which can be written as sum over n e to power, well, n e to power minus beta h now what is rho n? Rho n is n rho n. Actually, rho n m is equal to n rho m. This is what we called rho nm. Rho sum over all n and m, rho m. I just inserted two identities. This is n e to power minus beta h, or let me write it in a slightly different form. That is Kronecker delta nm e to power minus beta En, which I can also write as n e to power minus beta h m, because h acting on the Hamiltonian acting on m just gives me En, and what remains is a Kronecker delta nm. They are the same thing. And then again, I can use the identities. So this is divided by z, divided by z. So rho just becomes e to power minus beta h divided by trace e to power minus beta h. Now, the advantage of writing it as a trace is once I write it in this form, well, it's now independent of the basis, whichever basis you can use. In the energy basis, it's diagonal, but you can just use whatever basis you want. In particular, for example, we will be looking for the density of particles. Well, the density of particles will be given by the probability that your particle will be at a given position, but the probability that your system is in a particular state is just the corresponding diagonal matrix element. So it will be just the matrix element of rho between the Bra and Ketz at the position R. That will give you the density of your particles. And finally, let me write the grand canonical ensemble. Basically, it will be the same treatment as this canonical ensemble. And rho in that case will be e to power minus beta h minus mu n over trace of e to power minus beta h minus mu n. And mu is your chemical potential. Well, there is a catch here though. You see, we said that rho have to commute with the h, but we didn't say anything about rho commuting with n, or n commuting with h. So this is true if h and n commute. If the number of particles is conserved, then rho, the density matrix, is given by this expression. Well, what happens if the number of particles is not conserved? Well, it's not a problem if number of particles is not conserved. Again, if you remember why we introduced this coefficient mu, that basically made sure that the average number of particles was fixed. So we can just choose mu so that we fix the average number of particles. Just like beta, we had to introduce it to conserve the average energy, to fix the average energy of my ensemble. Mu we had to introduce to fix the average number of particles. But if the number of particles is not fixed, then like the photon gas, we will study the photon gas also, or the phonon gas, in that case mu is actually 0. So again, even if h and n do not commute, rho is still given by this expression, and it commutes with the Hamiltonian mainly because mu is 0. Let's do some applications of these. Up to here it might be somewhat abstract. Let's do an application. An electron in a magnetic field. Well, we know the Hamiltonian. We had already studied this system. This is the Hamiltonian is mu times sigma dot b. If b is in the z direction, h, the Hamiltonian operator, is minus mu times sigma z, which is minus mu sigma z b minus mu b plus mu b 0, 0. Now, what is e to the power minus beta h? Well, e to the power minus beta h, you see the exponents of operators, you always have to interpret them in terms of their Taylor expansion. This is n minus beta raised to the power n divided by n factorial h to the power n. Well, the Hamiltonian itself is diagonal, so its powers are kind of trivial to evaluate. Minus mu b raised to the power n plus mu b raised to the power n. Well, if you calculate, again, if you just evaluate these sums back, you would get e to the power minus beta h is equal to beta mu b e to the power beta mu b e to the power minus beta mu b 0, 0. This is e to the power beta h. The partition function q or z is trace of e to the power minus beta h. Well, the trace is trivial to evaluate now. It's a diagonal matrix already, so it's e to the power beta mu h plus e to the power minus beta mu h, or twice cosine hyperbolic beta mu h. The density matrix is 1 over twice cosine hyperbolic beta mu h times e to the power beta mu b e to the power minus beta mu b. This is the density matrix. Well, what is the spin of this system? the average of sigma z, let's say, the z component of the spin, this will be proportional to the magnetization, just multiply it by mu, you get the magnetization. Well, this will be trace of rho times sigma z. Rho is a 2 by 2 matrix, rho z, sigma z is a 2 by 2 matrix. This will be 1 over twice cosine hyperbolic beta mu h e to the power beta mu b, 0, 0, minus e to the power minus beta mu b, which is just sine hyperbolic beta mu b these are b's, divided by cosine hyperbolic beta mu b. Yeah, if you check your notes, these were actually what we had also obtained before. Now, if you look at the partition function, that expression over there, well, beta mu h is one of the possible energy, the energy of one of the possible microstates pointing in the direction of B, and minus mu B, so those are not H, those are B's. Beta mu B and minus beta mu B are the energy levels of the two microstates, so well, that is the familiar expression also, the partition function. So in a sense, we did recover what we had done before. But now at least we know that the framework is consistent with quantum mechanics. And also I would like to underline one thing. We are looking one electron. And now we will be looking at one free particle. In a box. Well, when we have more than one particle, things will start to get complicated. Well, we know the free energy. Let's look at the matrix elements of rho in position space for different r and r, different or the same r and r prime values. We have to calculate e to the power minus beta h r prime and then calculate its trace. So let's look at that matrix element of the exponent of the Hamiltonian. Well, it will be the easiest to calculate this in the energy basis, because then we don't need to worry about the exponent of the operator, but it will be the exponent of the energy eigenvalues. So I can insert an energy, a complete set of energy eigenstates. Minus beta E n. Now we will continue, but first let's just look at this expression. Now suppose we take the zero temperature limit of this expression. I mean, I didn't really specify what my state is, are there any interactions in my system or not, but whatever my system is, this matrix element will be given by that sum where n are the energy eigenvalues. If I take the t equal to 0 limit, well, that is beta goes to infinity, all those exponents will go to 0. But the ground state will go to 0 the slowest. So if you take a small enough temperature, all the excited states, they will not contribute to that sum. You will only have the ground state contribution. There will be a single exponent, and the coefficient of that exponent will be just your wave function. So in fact, this is one way of calculating wave functions or energy eigenstates of complicated systems. You just look at the expectation value of e to power minus beta h. Take the low temperature limit, everything will die off. The part that doesn't die off so fast will be your ground state. But let's stick with our free particle in a box. Now, what are my energy eigenvalues and energy eigenstates? My Hamiltonian is just p squared over 2m. My energy eigenstates will be given by e to power, I say I k dot r divided by square root of v. I'm using periodic boundary conditions. That 1 over square root of v is, I'm just normalizing to my wave functions to one particle within my box of volume v. And these k values can take any value between any value of this one, 2 pi over L times n, k, x, y, z, and x, y, z, where n, x, y, z can be 0, plus minus 1, plus minus 2, etc. So these are my energy eigenstates. So this matrix element of the exponent will be sum over all allowed values of nx, ny, and nz. Let me introduce delta nx, delta ny, delta nz, because all of these are 1. Nx, ny, and nz, they change by 1 as I sum over all of them. And then I have e to power I k dot r minus r prime, and e to power minus beta h bar squared k squared over 2m. Now, rather than summing over n, I will be summing over k's. Oh, sorry, by the way, I also have divided by v. This is the normalization of my wave function. Now, sum over nx, ny, and z, delta nx, delta ny, delta nz, is actually the same thing as summing over all allowed value of kx, ky, and kz. And delta nx will be just L over 2 pi cubed delta kx, delta ky, delta kz. I'm just making a change of variables. Now, delta n's were 1, but I'm in the thermodynamic limit. L is huge. So as I go from one kx value to the next kx value, or one ky value to the next ky value, the change in kx and ky will be suppressed by 1 over L, which will be negligible. So basically now I have a sum of many contributions of infinitesimal quantities, but that is nothing but what we call the Riemann integral. So now it became an integral. This is equal to v over 2 pi cubed d cubed k. I'm integrating over all possible values of k, of e to power minus beta h bar squared k squared over 2m plus I k dot r minus r prime. Now I need to evaluate that integral. Well, that will be, I will convert it to a Gaussian integral divided by v. So v's cancel. So what I have is 1 over 2 pi cubed d cubed k exponent minus beta h bar squared over 2m k squared plus 2m minus I 2mk dot r minus r prime divided by beta h bar squared. I just factored out some constant. Now let me add here, or subtract, add I m k over I m r minus r prime over beta h bar squared and subtract it. I'm just completing it to squares. That's the only thing I'm doing. So that matrix element (1 over 2 pi cubed) d cubed k exponent minus beta h bar squared over 2m k minus I m r minus r prime over beta h bar squared, all of these things squared. It's just the first three terms, these three. And then I have the last term is minus m r minus r prime divided by beta h bar squared 2, and this one squared. Yes. Now the k integral just 3 Gaussians. If you like, you can just shift k by I m r minus r prime over beta h bar squared. It just becomes a symmetric Gaussian in that case. So this is 1 over 2 pi cubed pi over beta h bar squared over 2m raised to the power 3 over 2. This is the result of the Gaussian integral times the exponent minus mkt over 2 h bar squared r minus r prime squared. This is the matrix element of the exponent appearing in my density matrix. I need to evaluate the trace to obtain the density matrix. So the trace of e to power minus beta h, the trace is nothing but the sum of the diagonal elements in whatever basis you are using. Well, the diagonal elements is r e to power minus beta h r. This is the diagonal element. I need to sum over all r times d cubed r. But that is just 1 over 2 pi cubed 2mkt pi over h bar squared raised to the power 3 over 2 times v. Because if r and r prime are equal, that the exponent is just 1, there are no r dependents. So the integral over r just gives me the volume. And now I have my matrix element of the density matrix. 1 over v times the exponent minus mkt over 2 h bar squared r minus r prime. This is the density matrix of a free particle in a box of volume V. Well, the diagonal elements, as I said, give us the probability that or in this case, the probability density that the particle will be at that location. Well, the probability density is just 1 over V. It just tells me that, okay, the probability distribution of my particle is uniform within my volume V. That is expected. I have a free particle. It doesn't prefer to be here or there. So on the average, it will be everywhere. And 1 over V is just a normalization of the total probability to be 1. I have just one particle.
distance square, right? R minus
Yes, yes, sorry, that is squared. Well, if you look at the off-diagonal elements, well, they basically, they measure, in a sense, the spread of my particle, or the correlation of my particle to be in one position or the other one. And if you see let's say that, let me write this in this form, exponent of minus r prime squared divided by 2 lambda t squared, where lambda t is h bar over square root of mkt, which is sometimes called thermal wavelength. Yeah, you will see various definitions of the thermal wavelength with various factors of pi or 2's. Now, what is it the wavelength of, or why is it the thermal wavelength? Well, we have a free particle. The energy of my particle, which is p squared over 2m, which should be the energy, if the energy is the thermal energy, this will tell me that p squared is of the order of mkt, or p, the momentum, is of the order of mkt. So if you have a particle at temperature T, typically your particles will have this much momentum. But the corresponding de Broglie wavelength is h over momentum. This is the corresponding wavelength. As I said, depending on the definition, you get 2's, pi's here and there, but the order of magnitude is this one. So in a sense, this is how much your particles are localized or not localized in the system. For example, if you take the limit, low temperature limit, well, what happens in the low temperature limit? No, in the high temperature limit, let's say. In the high temperature limit, the thermal wavelength basically goes to 0. You have localized particles. If you look at this one, or this expression over here, in the high temperature limit, T is very large. So whatever multiplying T should be sufficiently small for it to be non-zero. So the spread is basically minimized in the high temperature limit. Well, that is what we expect. We expect to recover the classical result. Classically, if you would like to write something like a density matrix, it has to be diagonal. And the other extreme, if we take the t goes to 0 limit, the exponent basically becomes 0. We have the 1 over v. The particle is kind of everywhere. And remember what I said, if you take the t goes to 0 limit, at least you get the absolute value of the wave function squared. Well, absolute value of this wave function squared is 1 over v. Well, that is our normalization. 1 over square root of v. Any questions? Now, in the next hour, we will repeat this derivation also for the harmonic oscillator. Basically, the idea is the same as the one we used over here. If you want to calculate the position space matrix elements of that exponent, e to power minus beta h, first you write it in terms of energy eigenstates. And if you know the expression, you just need to find out what the wave functions are in the energy basis. once you know that, you have to carry out that sum. Well, I will skip most of that technical computation, just write the result, but we will then discuss what the result tells us. And then, okay, these will be all single particles. The real question we would like to address is, what happens if we have more than one particle? We will start with 2 particles, and we will start today with 2 particles, and probably in 10 days after next week, we will just generalize. Any last minute questions before you go for a break? So let's meet in 10 minutes.